3.3a is types of discontinuities. Okay, so first you have this kind. We're kind of going along, and then there's an open spot or a hole. And this is a hole, also known as a removable discontinuity. This shows up when we have our 0 over 0, our indeterminate form, where if we were finding the limit, we would, be able to cancel it out. Another type is where let's say you go up to here, there's a hole, and you jump up here, and it continues. There's another one similar to this. Sometimes you go along and you have a hole, but the actual point is up there. Those are both called a step discontinuity. And we also have, say there's a vertical asymptote right here, and then your curve does that, maybe that, and this is called an infinite discontinuity.
So I just put my headphones in, so the sound quality may have been iffy for the first 2 minutes, but from now on, hopefully it'll be better. Okay, let's talk about a graph that looks like this. Say it kind of goes up and goes back down and makes kind of a point at the top. That's called a cusp. And a cusp is a point, and let's just write cusp here, right? A cusp is a point on a graph that is continuous but has no slope or instantaneous rate of change. Because if you think of looking at a slope at a point, if you just draw a line, so if you had a curve, say, like that, you could draw a line right there and be like, oh, the slope at that point looks about like this. But if you did it for the cusp, are you going up? Are you going down? It's kind of like a teeter-totter, so you don't know if you're going up or down. And this will make more sense as we go on. And just remember, a continuous function can be drawn without picking up your pencil. Okay, and again, if the cusp thing is kind of throwing you, what do you mean it doesn't have a slope? For now, just know that's a cusp and it doesn't have a slope. If you don't know why yet and don't quite understand, that is not a problem. It will become clear in later lessons. Now let's talk about the continuity test. The continuity test states that a function f of x is continuous at c if and only if, just a little side note, so this and IFF mean if and only if. Plus I have an excuse to use my pretty rainbow color. Okay, A function f of x is continuous at c if and only if, number one, f of c exists. Number two, the limit as x approaches c of f of x exists. And number three, f of c is equal to the limit as x approaches c of f of x. And again, continuous means you can draw it without picking up your pencil. You can draw the whole function. So for example, a lot of times we'll see piecewise functions, and basically we're looking at if they connect and whether or not there are holes. It's kind of what the continuity test shows us. So f of x equals x plus 4 when x is less than or equal to 2, negative x squared plus 8x minus 8 when 2 is less than x is less than 5, and x plus 2 when x is greater than or equal to 5. So now we will test for continuity. Just like before we checked the limits, now we're going to do the whole continuity test at 2 and 5, because that's the numbers we see over here on the right, or where the function changes definition. So first, continuous at 2, question mark. I have really weird question marks, so look like 2s with dots. If I've taught you before, you'll recognize those. If not, don't waste your confusion. Those are just my weirdo question marks. So number 1, let's see if f of 2 exists. So f of 2, since x is less than or equal to 2 for x plus 4, 2 is included. So f of 2 is 2 plus 4, which is 6. It exists. Check, that one's okay. Number 2, we have to find the limit, so to check both sides. So the limit as x approaches 2 from the left of f of x, from the left is less than or equal to 2, so that's x plus 4 again. So 2 plus 4, which is 6. The limit as x approaches 2 from the right is going to be just greater than 2, so it's this middle one where 2 is less than x is less than 5, or x is between 2 and 5. So negative 2 squared is negative 4 plus 8 times 2. So negative 4 plus 16 is 12 minus 8 is 4. So 6 and 4 are not the same number, clearly. So the limit as x approaches 2 of f of x does not exist. So then the continuity test fails right there. F of 2 exists, but the limit does not. So it's not continuous at 2. So we just say no. Now let's check if it's continuous at 5. First of all, let's check f of 5. Does that exist? It looks like 5 is included for x is greater than or equal to 5, or x plus 2. So f of 5 is 5 plus 2, which is 7. So we're okay there. Second step, let's take the limit on both sides. So the limit as x approaches 5 from the left of f of x. So that's going to be the between 2 and 5 function. So negative 5 squared is negative 25, plus 8 times 5, which is 40. Negative 25 plus 40 is 15, minus 8 is 7. Okay. Now the other side, the limit as x approaches 5 from the right of f of x, from the right is going to be greater than or equal to 5, so the x plus 2, 5 plus 2 is 7. So now, the limit as x approaches 5 of f of x, since both sides is 7, the limit's 7. So step 2 passes as well. Step 3, we're looking at basically the answers to 1 and 2. Are they the same? So they are, right? Because f of 5 is equal to the limit as x approaches 5 of f of x, which is equal to 7. So we're good. So we passed all 3 parts of the continuity test. So the answer is yes, the function is continuous at 5. Something to consider. A function can be continuous on an interval if and only if it is continuous for every every value in that interval. It's a terrible box, but I'm going to leave it. So what this means is if we look up here at our piecewise function, we checked it's continuous at 5, but it's not continuous at 2, meaning f of x is not continuous on the interval from 2 to 5. That's kind of what we're getting at. So as soon as anything is not continuous, there's a hole or a discontinuity of some sort, doesn't work anymore, as continuous at least. Okay, last thing we're going to do is talk about how to remove a hole or removable discontinuity, or in terms of how can you write a function that accounts for that, because removing it, you basically just cancel it out, right? So let's say we have the function g of x equals x squared minus 9 over x minus 3. So if we factor this, kind of checking for holes really is what we're doing here. X plus 3, x minus 3 over x minus 3. So these cancel out, so we have a hole at x equals 3. So now, if we take the limit as x approaches 3 of g of x, all we're left with up here is x plus 3. So the limit as x approaches 3 is just 3 plus 3, which is 6. Point being, our function will look something like this. This is 3, this is 3, this is 6. We know there's a hole at 3, but the limit is 6, meaning it looks like it should be 6. So maybe the function does that, okay? Maybe it looks like that. So we can write an extended function and basically make it piecewise and say f of x equals x squared minus 9 over x minus 3 whenever x does not equal 3, because this function is fine. We just have a hole at 3. And when it is 3, we get what we got. We get what we got. Oh my goodness, you guys. We had x plus 3 when we simplified and cancel out our hole. So the function is just x plus 3 when x equals 3. So this is what we call an extended function. And it really just explains the graph better. Because really it says, okay, x squared minus 9 over x minus 3 is the function, but then we have a separate piece to account for the hole in the graph.